Hello there. Today I want to show you how to use the Superluminal profiler with Unity. This applies to both the Unity editor and the build of your game made with Unity. But I'm going to be focusing on the editor because it's the same workflow, it's a little bit easier, and quite frankly I care more about editor performance than about game performance, which may sound counterintuitive, but I think that's where it really counts. Just make the process enjoyable of making games. Probably says more about me than about Unity. Anyway, the Superluminal profiler is a tool for Windows that allows you to do sampling profiling on Windows and on console. We're going to be focusing on the Windows case here, and we're going to use the example of the entity samples on 2020.3, but Superluminal works with all of the latest releases in the 2020, 2021, and 2022 range. Before we open the project, the first thing to make sure is that we go to the advanced project settings and add this command line argument, monoprofiler Superluminal. So that's dash mono profiler in capital, like in the first letter capital, and then space Superluminal. And then we open the entity samples project, which is going to take a second. And while this is opening, I'm going to be showing you Superluminal. This is Superluminal. First, make sure that you familiarize yourself with this setup here on the left, where you have the attach, run, and session explorer. What we're looking at is the attach one. First thing to note is go to the tools settings and take note that there's a controls tab. You're probably not going to want to look at it immediately, but make sure you're aware that it's there, because at some point you're going to want to change the controls of the tool. You can see mine is set completely to custom. And then the other thing is the general tab. In the general tab, you can set up symbol file locations, so usually a symbol server. What do you need a symbol server for? So Superluminal is a sampling profiler, which means it's going to use some Windows kernel facility called Event Tracing for Windows, ETW, to stop your processor around 8,000 times per second, like 8 kilohertz. It's a little bit more than 8 kilohertz actually. And this will give you an ETL file. It happens all behind the scenes, you don't have to know this, which contains call stacks, which is just a list of addresses saying, hey, at this point in time, this thread was doing work at this address, and these are the other addresses on its call stack. And at some point you want to map these addresses back to something that is actually sensible for humans, like function names or even line numbers, and you want to see, oh, this address actually corresponds to that function. That's what you need symbol files for, or PDBs, program databases. There's the symbol files for your own game. What you want to do with that is you probably want to click this folder icon and add the path on disk to your own game to the symbol file locations. And then there are the Unity symbol files. If you look in the Unity documentation for symbol files or symbol server, you're going to find a link to http://symbolserver.unity3d.com. That's a public symbol server. If you're watching this and you are a Unity employee, there's also an internal one. The difference is that the internal one has full symbols and the public one has stripped symbols. For the sake of this example, we're going to use the public one. Okay, now we are going to attach to Unity. You're looking for the Unity process. You can also do that by just using this find thing. You can see you've got recent processes and all processes. Right now there's only one process, but frequently when you're trying to profile the editor, there are going to be two. You're going to look for the one which actually has a window title that corresponds to your project. There might also be a Unity process around without a window title, which is just the asset import worker in the background. So Unity has, since a few versions now, this feature of spawning a copy of the process in the background. And this copy is only doing asset imports, so it doesn't block your main process. Now, we're going to double click this now, and you're going to see a first problem. Oh, before we do that, make sure you have start profiling immediately enabled down here. Double click it, and we are getting a prompt from Superluminal. Haha, because Superluminal detected that this won't work, what we're trying to do here, because we're trying to profile a Unity application. We need to use Superluminal's secret, well, not so secret, plugin for that. So what it says is the Unity application you're profiling is missing the Superluminal plugin. To enable profiling of managed code in Unity, make sure that the monoprofiler Superluminal DLL plugin located here is copied to the folder that contains Unity's executable. So either next to your editor or next to your game. Let's click the here link. There we go. There's the monoprofiler Superluminal. In my case, I'm just going to open the hub. I'm going to go to the installs, and I'm going to go here and then click show in Explorer. Now I see where my unity.exe is. I'm going to take the monoprofiler Superluminal. I'm going to put it right next to it. Yes, I'm willing to copy that, and now I'm going to close all of this again, click no, because now we need to restart Unity. Okay, let's do that. Now this is, by the way, exactly why we need this monoprofiler Superluminal command line, because now we copied the DLL to the right place. Now with this command line, Unity will know to actually look for that DLL and load it. Okay. Now it takes a second to do this. Why do we need that plugin? I told you about symbol files and the fact that we get this stream of different addresses that represent what a process is doing. That works very well for properly compiled code like native code, C++ code, but not so well for Mono code, because Mono, C#, in this case, like the Mono runtime is powered by a JIT compiler. The JIT compiler will only figure out where to put certain code at runtime. So there's no symbol file that tells us, oh, for this address, that's that function, because we don't know the address until we actually compile the function. So the plugin will add extra information whenever something is JIT compiled. It doesn't have any cost when you don't use it, so there's no harm in having it there. But it's necessary to get to resolve symbols for managed functions. So if you run Superluminal and you don't see your own managed functions, that's because you forgot that the DLL or the command line argument. Okay, so what are we going to profile? What we're going to profile is this Boyd scene from the empty samples. We're going to click enter play mode, and you can see these are the Boyds. There's the shark coming through any moment now. There's the shark, and then we're going to go back. And the way that we do it is make sure start profiling immediately, select it, double click unity.exe, give it the right privileges, because as I said, it needs kernel stuff to do the actual sampling. And now click play, give it some time. So you can see here we're currently sitting at 12 seconds, maybe wait until 30. The reasoning here being that a sampling profiler is a statistical tool. Compared to Unity's profiler is an instrumentation-based profiler, so we have to explicitly insert markers, and that allows us to measure something on like a nanosecond scale almost. A sampling profiler, click start analyzing when you're done, works differently because it stops the CPU all of the time. This comes with some overhead, and in my testing that's like between 8 and 10%, so it's not free but also not crippling, and also it's very uniform, so it doesn't distort the data too much. But because of this statistical nature, you're always better off having more data, and what am I going to say? Especially when you look at different frames, every frame is only like 16 milliseconds, so you need a bunch of frames to get enough data to make any kind of statements. But we'll look at that in a second. So here is the Superluminal main view. Time is on the horizontal axis. Threads are going from top to bottom, so you have the different threads here. When a thread is green, like the main thread here, it's doing actual work. It doesn't say it's sensible work, but it's doing work. Red means it's spending its time on synchronization. There are a few other colors, they are less important right now. And the threads here are roughly sorted by how much work they are doing. So you can see the most green thread is the main thread, unity.exe, that's at the top. Then we've got 16 job worker threads. Then we've got the Unity GFX device worker thread, that's like the graphics thread. And then we have a bunch of random threads below. So Unity applications always have many, many threads, especially when you're running it in the editor. And the first thing that we should probably do is we should click the first thread below the Unity GFX device worker thread, because we're not interested in it. Then we're going to scroll all the way down we're going to hold down Shift, click the last thread to select them all, and then we either click this hide all selected threads button or we just press delete. And they're gone. If we accidentally delete something that we shouldn't have deleted, just use this I up here to unhide it. Okay. Now, whoops. What you can see here now are the different threads, and we're probably mostly interested in the main thread because the job worker threads, I suppose. You can collapse and uncollapse it, and then you can see all of the work, and you can see here's a big white or blue bar depending on your theme. This is the dark theme of Superluminal, and you can see sometimes this bar has a name in it, sometimes it doesn't. Don't worry, it's just a matter of whether you're zoomed in enough. And first thing to note is this is super snappy. This feels great. So Superluminal has an awesome user experience, if you ask me. So what you see here is the call stacks. So you can see we start by calling user thread start. That's just how running a thread on Windows works. And at some point we're in the main message loop, and we spend all of the time in the main message loop. But after that, it kind of diverges. We call different things, call application.tick timer, and then in between we also call profiler session.editor tick apparently. Okay. So there are various ways in which you can use a tool like this to detect problems. The first thing is, like, we're probably going to look at the Unity main thread again. And the first thing that I'd like to show is something that I'd call qualitative profiling in this case. So what do I mean with qualitative? What I mean is we know something is slow. So for example, we know that maybe entering play mode is slow. What we can do is we can hit Ctrl F and we can just look whether there is something that's called enter play mode, and there is. And it's been highlighted for us. Superluminal found it, and it's going to also jump to it. And we can see this takes like 344 milliseconds to do. Remember, we're sampling at 8 kilohertz. That means 344 milliseconds. That's roughly about a third of a second. So we're going to take a third of the 8,000 samples. So we've got, I don't know, 2,000, 3,000 samples in this range here. And every sample represents like 120 microseconds of work. Now we can look at it and we can see, oh, it spends a lot of time in GC collection at some point, and now we know GC collection is slow, and now we can look at why it's slow, and so on and so on and so on. But maybe that's not a good example. What I'd like to instead look at is maybe the add system on create internal. So this is something that the entities package is doing. It's 83 milliseconds. 83 milliseconds, that's still enough, I think, to make sense of the samples. Let's click it, and then the workflow would be, you found something that's slow, and now you look at, you click it in here, and you look at the source and disassembly window and see why it's slow, and then yeah, you can see it's a create instance that's slow, and so on and so on. I think this workflow is fairly self-explanatory, because now you've got like this call graph on the left, and that's centered around the onCreate internal. Now you can step into it and look where you're actually spending the time and so on. But this is not actually, I think, the most useful workflow for a tool like Superluminal, because as I said, it's a statistical tool. And especially when you look at a game or anything, any repeated process that has many frames, or many, like you're processing many things one after the other, there's often not one thing that is slow, but there are many things that are slow. And the Superluminal profiler, or a sampling profiler in general, might be misleading when it comes to that. So if I just look at a single frame, so you can drag these selections, and when you drag the selection, everything else in the profiler will be like relative to that selection, like the times and so on. You can see in the call graph down here, no worries, we're going to talk about that in a second more. This is like 12 milliseconds. 12 milliseconds, given that we do like 8 samples per milliseconds, That's like 100 samples in total. That's not necessarily representative, because 100, like just looking at 100 times that what happened during that frame, it's not going to tell you the whole story. It's going to be a lot of randomness in there. There's like all of the goodness that you may remember from your graphics class about aliasing and Nyquist theorem. It all applies. In this data, there's a lot of aliasing, because the things that are actually happening happen at a much higher frequency than what we can sample at. So you have to be careful in what you do with a single frame. And especially if I now zoom in and see, okay, we're now spending a lot of time in unityxe.get work stealing range. And I hover this and it says 15 microseconds. It doesn't actually mean that it's 15 microseconds. It just means there's a sample, and the next sample happened 15 microseconds later, which is already a special case, because usually samples are 120 microseconds apart. In this case, there's like a special sample that we get for something that's, yeah, let's not talk about that. Point is, when you have something here and it takes 120 microseconds, it almost never means anything meaningful. And this qualitative looking at stuff might work for something like you have something that takes hundreds of milliseconds or even seconds. Great. But as soon as you look at like, ooh, this is taking like fractions of a millisecond or just 1 millisecond, it's going to be misleading. Instead, what you want to do is you want to look at the entire range of where you run your program doing the meaningful thing, like running the frames, and you want to take a statistical approach. And how do you do that? Because now it's like I've selected all of this range here, that's 25 seconds. The way that you do it is you just click in one place and you drag to another place, and if you want to cancel the selection, you just press escape. How do you make sense of this much data? Because it's 25 seconds of data, 25 times 8,000, that's a whole lot of stuff. Like, how much is that even? It's like something like 2 million samples, something like that. Maybe even more, 20 million. Don't nail me down on the specific. It's too much to make sense of manually. And while the qualitative looks that we've given it might be helpful to inspire some investigation, we should really use this window down here to do our work. There's the call graph and the function list and the thread interactions tab. I think the interesting ones that we want to look at is call graph and function list. Call graph is a top-down view. It means we can just follow whatever is the most expensive call down the call stack in the same way that the program flows, and we can figure out what is slow. And we get this wonderful representation where you can see, oh, we spend so much time tick timer. You can see it's up there, and as I walk down the stack, you can see we're going to the highlight shifts, and it's going to be more and more fractured. And in the end, we can see, okay, it's probably spending like 5 of these 25 seconds in parent system.update, which is also something that you can see qualitatively, because yes, a large part of the frame seems to always going to the parent system.onUpdate, so that makes sense. What you then need to figure out is, why is the parent system slow? Then you can use either this view or like the source and disassembly view, or just try to dig down further. In this case, you see, okay, it's probably calling into a job, and the job is doing some things, and you can look at what the job is doing. But really, I think there is something to be said for this kind of analysis, but it's not what I would recommend for these kinds of, I've got 30, like I've got a game running at 30 FPS, 60 FPS, and I want to figure out why it's slow. It's probably not the right approach. Before we move on, I'm going to explain two or three more things. The first is, in this view, you've got the function name, the module, which is just like which DLL does it come from, and then you get the inclusive time, the exclusive time, and the thread state. The thread state kind of tells you, hey, below this function, how much time is it actually doing work, and how much time is it sleeping or doing inter-thread communication. The inclusive time means, for this specific point in the call stack, how much time is spent in that call and all the things that it calls. Like if you were to measure, like put a marker before it and after it, and you have, assuming you have enough samples, what would be roughly the time that you get? But then there's also the exclusive time, which means how much time do you actually spend in this specific function, disregarding everything that it calls. So these are two important things to note, the inclusive and the exclusive time. And ideally, the dream is that you find something that has 100% exclusive time, where it's like all of the work is going to that function. I just need to figure out what that function is doing, make it faster, or like really make it stop doing the incredibly stupid thing that it's probably doing. But that's seldom the case. So the things that are still worth knowing about is there's this button to expand the hot path. A lot of people do that, I find, but I don't find it very helpful. What it's doing is like it's taking the call stack and always taking like the most expensive call that you make, and then you walk all the way down to the stack until you are at the very bottom. Why don't I think it's helpful? I don't think it's helpful because at some point you end up at something like TLS get value, like it's trying to get a dynamically allocated TLS value. Okay. And it's spending 24 milliseconds on that. Should it? Well, it probably shouldn't. Luckily, this is editor-only code, so no excuse. It probably still shouldn't do that. But it's not necessarily what you want most of the time, because you don't even know whether does it only happen here? Is it just this specific case where this TLS get value is called and so on? So this hot call tree or hot path, it's geared towards this case where you have one function that takes a lot of time, which is often not what's happening, because that function usually calls other functions. The other thing that you can do is you can say, oh, there's a lot of repeated work. So for example, you see that up until we get to the player loop controller update scene, basically this pie chart in the middle shows us we are probably almost spending 99% on the same thing. So there's very little information on the top parts of the call stack. So what you can do is you select whatever you want to be the root of your call graph, and you click set as root, and now it's the root. And you can also, of course, undo that either with that button or by right-clicking it again. Okay, now to the second window, which I think is the more relevant window. That's the function list. The function list is throwing away all of the structure that you had in the data as a first step. Like the entire call graph is irrelevant to this first part of the function list. And it just asks you, no matter how I ended up calling a specific function, how much time am I spending in that function? And now you can see why that is juicy, because the problem with the that I just talked about with the TLS get value is like there could be many ways that we call that TLS get value. There are many different call stacks could end there. The call graph won't show us, but this one will. And my favorite way to use this as a first way to get some information out of it. It's definitely not like, this is not the entirety, but it's a good start always, is to just sort by exclusive time and pick the top of the list, and see the top of the list here is exit dispatcher from the kernel module. Now we won't be able to do anything about kernel code, but what we can do is we can make sure that it's not called as often. That is one thing that we can do. And you can also see this is exactly the case. It's called all over the place. There's no single call tree that is going to cause this, because we're going to end up there in different ways. So once you selected, the middle thing here lights up, and also the thing on the right. The thing on the right here is the disassembly, because for the kernel we don't have source code, and you can see where the different samples land. So in this case, again, we're looking at something that takes 7 seconds in total, or meaning it has the equivalent of 7 seconds worth of samples, where every sample is 120 microseconds. So we have a lot of samples here. So these numbers that you see here, like 3.2%, 96.8%, they actually make kind of sense, because we have enough samples to have confidence that these numbers mean something. Still, when you look at the disassembly, I would highly suggest not looking at a specific line. So for example, it claims that it spends 97% of the time executing a NOP. A NOP is another word for not an instruction, no operation. Nothing is happening here, and I find it hard to believe that it's going to spend 97% of the time here. What you have to remember is, when you look at disassembly, A, maybe you should use another tool, because this tool doesn't really give you any like instruction level insight. So you could use, for example, what do I know, Intel's VTune, which is painfully slow, but sometimes that's what you have to reach for, unfortunately. The other thing to remember is, if you look at the disassembly, and sometimes you will have to, don't pay exact attention to the specific line that something falls into, because the specific line is probably wrong. That's also because there's a lot of aliasing into where you actually, like, what line something gets attributed to. So the way that the sampling is implemented is using hardware interrupts, and the hardware interrupts are just not equally likely to trigger at all the different places. There's a great article by Travis Downs about this. Downs? Either. So yeah. Now, but back to the middle part of the function list, because that is where it's get juicy. So at this part, we reintroduce the call stack information, because we can now see, hey, there are different ways how we end up in the exit dispatcher, and the top way that we end up in the exit dispatcher code is by somebody calling release semaphore, and because we get there because somebody else called NT release semaphore, and blah 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 blah, a bunch of system calls later. We see, oh, at some point somebody calls baselib system semaphore release, and after that things kind of split up. Now there are very many different reasons why we get that, but still, using the bottom-up approach, we were able to figure out, okay, we spent all of this time on somebody releasing semaphores. If you have no idea what that means, it essentially means there's somebody, like, we're paying a heavy tax for a thread interaction. On the main thread, somebody is repeatedly using a semaphore to signal to another thread, hey, you should do some work, because that's how the job system works in 2020.3. The overhead that we're paying here is completely unreasonable. Like if out of 25 milliseconds, paying 7 milliseconds on that on job system, it's not just job system overhead. Let's be fair here, but it's different kinds of inter-thread communication. That's not reasonable. That's also a problem that is known, and that Unity is actively looking into fixing. I won't talk about any specifics here because I shouldn't. But yeah. So yeah, at this point now you know who's calling this, what different ways there are, and you know either avoid calling these functions or make this function better. Or in this case, we learned, hey, maybe we should restructure how a lot of these thread interaction things actually work. Okay, then we should probably also briefly talk about this last one, the thread interaction window. This is again something that makes more sense on a qualitative level. So let's look here. We have one of these cases where we call the semaphore release because somebody scheduled a job, and you can see all of these dashed lines. What these dashed lines are thread interaction markers, meaning that, hey, some thread interaction is happening here. And that's no surprise because we release a semaphore because somebody scheduled a job. And when somebody scheduled a job, that means the main thread tells the worker thread that it needs to do some work. So that's a thread interaction, one thread telling another thread to do something. It's in fact like this calling release semaphore triggers that interaction. If we click one of these dashed lines, we can see exactly what's happening here. We see a blocking call stack and an unblocking call stack. The blocking call stack here is saying, hey, the job worker thread was blocked for 8 microseconds, so not a lot of time, because it waited for more work. And then the unblocking call stack is, you can click that to go back to the unblocking call stack, get to the blocking call stack. The unblocking call stack is the main thread saying, okay, I'm done, or I have more work, please do continue. So yeah, this is useful in, I'd say not so much here because these blocking states are all very short, but it's generally helpful to know that this exists. Okay, now I think this is giving you the gist of the thing. I want to just give a few more shoutouts. The first one is this up here. The names that you get for the traces are never helpful. Do yourself a favor and rename them to something useful. Second, this is Unity specific. When you look at the different modules, you sometimes find modules with really nonsensical names, like long hashes of something. these are almost always burst, or not almost, these are always burst compiled functions, and it's just the way that these things end up being named is like that. And burst functions are interesting because you see C# code here, but you can actually switch to the disassembly. Usually with usual C# code that's not burst compiled, you cannot switch to the disassembly because disassembly is not known anymore once the program is shut down because it's JIT compiled. Here you can, and for burst code you actually often have to. Why am I saying this? Because this burst code here, for example, is a job. This job has some scaffolding code, and then inside of there, this is where it's actually calling your job data, or your job function. Burst aggressively inline stuff, and if you look at the, like, okay, it's spending 97% of the time in the execute, and then you look over here in the calls list, what stuff does this thing that we're seeing call? You don't see the execute method. Why don't you see it? Because burst decided to inline it, and the only way to be able to then reason about the code is to look at the disassembly. And again, here it's incredibly important to take into account how many samples do I actually have, and should I really care about the specific line that a sample falls into. But this kind of looks harmless in many cases, so there's, like, we can argue whether this is good code, and I really don't know because I haven't read it, but it, like, this is kind of what you'd expect usually. Like, it's lots of cost smeared across a few assembly instructions. If that's not what you're seeing, like the typical cases when something really falls onto a single assembly instruction, again, don't look at what that assembly instruction is doing, but there's a good reason why it's exactly that instruction. It's usually that some instruction in the vicinity is accessing memory and you're observing cache misses, and some aliasing then makes point to that specific instruction. But yes, so oh yeah, I should also tell you that what we did so far is we just looked at the main thread, but what we can also do is, like, we can again select multiple threads, and both the call graph and the function list, they also work across multiple threads. Great. I think the only thing that's left is closing words. So closing words, what is really important to take away? Superluminal is a sampling profiler. Sampling profilers are statistical tools. Make sure you always look at the sample counts that you have and profile longer sessions. Second, when you look at this assembly, never look at the specific instruction that you get. Third, make good use of the function list. That should probably be your first line of defense. Just function list exclusive time is going to tell you a lot. Fourth, make sure to use the plugin and set up the command line argument, because that's really how you get managed symbols. And if you get a lot of unresolved symbols, like, what does the unresolved symbol look like? Do I have any here? Here, like this one. This one, it says it's from an unknown module, and it has only an address as a name. That's an unresolved symbol. If you have many of those, it's probably because you're either calling into some code that you don't have the PDBs for, the symbols for, or because you're missing something on the command lines or the plugin. Okay, that's it. Thank you for watching. I hope this was informative. If you have any more questions about Superluminal, then please do reach out. I'm happy to answer them. Bye.